the universe that refuses to tick. Hi there, and welcome to Sleep and Learn. Tonight, we begin an extraordinary journey into one of the deepest mysteries of modern science: quantum entanglement and the illusion of time. As you settle in, allow your breathing to slow. There is no puzzle you need to solve tonight. Instead, imagine yourself stepping into a vast cosmic library, where every shelf contains ideas that have challenged humanity's greatest thinkers. In this quiet place, curiosity replaces certainty, and every question leads to another, even more fascinating one. For most of human history, time seemed wonderfully simple. The sun rose in the east and set in the west. Seasons followed one another with dependable precision. Children grew into adults, mountains slowly weathered away, and civilizations rose and fell. Time appeared to be the invisible river carrying everything forward. Ancient civilizations measured it by shadows cast from stone pillars. Sailors trusted the stars. Farmers relied upon the changing length of daylight. Eventually came mechanical clocks, pendulums, precision chronometers, quartz crystals, and finally atomic clocks so accurate they would lose less than a second over billions of years. Every improvement reinforced the same comforting belief: time was fundamental. It existed independently of us, flowing smoothly through the universe like an endless current. Then, during the 20th century, physics quietly began dismantling that picture. The first surprise came from Albert Einstein. According to his theory of relativity, time is not universal. Two observers moving differently, or experiencing different gravitational fields, can measure different amounts of time between the very same events. An astronaut traveling near the speed of light would age slightly more slowly than people remaining on Earth. A clock placed atop a mountain runs ever so slightly faster than one resting at sea level because gravity itself influences the passage of time. These predictions sounded almost impossible when Einstein first proposed them. Today they are confirmed every single day. The Global Positioning System, or GPS, must constantly correct for relativistic effects. Without accounting for the tiny differences caused by both Earth's gravity and the satellite's enormous speed, navigation errors would grow by several kilometers every day. Time, it turned out, was already stranger than anyone had imagined. But relativity was only the beginning. At nearly the same time, another revolution was unfolding. Scientists studying atoms discovered that the microscopic world followed astonishingly unfamiliar rules. Instead of tiny billiard balls moving predictably through space, electrons behaved like both particles and waves. Light refused to choose between being a wave or a particle. Energy came in discrete packets called quanta. Probability replaced certainty. And beneath everything lay an invisible mathematical framework unlike anything classical physics had ever described. This new understanding became known as quantum mechanics. Its equations predicted experiments with astonishing accuracy. Yet the picture they painted of reality seemed almost dreamlike. Perhaps nowhere is this more evident than in quantum entanglement. Imagine two particles born during the same microscopic event. According to quantum theory, these particles may become linked in such a profound way that describing one separately from the other becomes impossible. Together they form a single quantum system, even if they later travel to opposite sides of a laboratory, or eventually to opposite sides of a planet. Measure 1. Instantly, the mathematical description of the other changes as well. Not because information has necessarily traveled faster than light. Modern experiments and theory preserve Einstein's speed limit. Rather, the particles share relationships so deep that ordinary ideas of separation no longer seem sufficient to describe what is happening. This phenomenon disturbed Einstein enormously. He referred to it as spooky action at a distance. To him, nature ought to possess clear, local properties. Objects here should not depend upon measurements performed over there. For decades, many physicists suspected that quantum mechanics must be incomplete. Perhaps hidden variables, still undiscovered, governed these mysterious behaviors. Then came one of the most elegant scientific tests ever devised. In 1964, the Northern Irish physicist John Bell developed a mathematical theorem capable of distinguishing ordinary hidden variable theories from genuine quantum predictions. Bell's inequalities transformed philosophy into experiment. Beginning in the 1970s and continuing with increasingly sophisticated technology through the following decades, laboratories repeatedly tested Bell's predictions. Again and again, nature sided with quantum mechanics. The results consistently violated Bell's inequalities exactly as quantum theory predicted. Entanglement was not merely a mathematical curiosity. It appeared to be woven into reality itself. Today, entanglement is no longer an abstract concept discussed only in university lecture halls. Scientists create entangled photons using lasers. Researchers entangle trapped ions inside electromagnetic fields. Superconducting quantum processors manipulate dozens or even hundreds of entangled quantum bits, or qubits, allowing entirely new forms of computation that classical computers struggle to imitate. In 2017, China launched the satellite MISHUS, successfully distributing entangled photons across distances exceeding 1,000 kilometers. These experiments demonstrated that quantum entanglement survives astonishing journeys through space, opening the door to future quantum communication networks. The universe, it seems, is far more interconnected than our everyday experience suggests. And yet, hidden beneath all these discoveries lies an even deeper mystery. What if entanglement is not simply something that happens within space and time? What if it helps create them? This remarkable possibility has become one of the most exciting frontiers in theoretical physics. Several modern approaches to quantum gravity suggest that spacetime itself may emerge from more fundamental quantum relationships. Rather than existing as the stage upon which particles perform, space and perhaps even time could be products of an underlying quantum architecture. Imagine looking at a magnificent tapestry hanging in a museum. From across the room, it appears perfectly smooth. Approach more closely, and intricate patterns become visible. Move closer still, and individual threads emerge. Finally, under a microscope, those threads reveal countless tiny fibers twisted together. At every scale, the object appears different, yet each level emerges naturally from the one beneath it. Some physicists suspect reality behaves in much the same way. What we experience as continuous space and flowing time may be like the tapestry viewed from a distance. Beautiful, coherent, and entirely real in everyday life, yet ultimately emerging from unimaginably small quantum connections that possess no familiar notion of distance or duration. If this picture proves correct, then the ticking clock beside your bed is not measuring a fundamental ingredient of existence. Instead, it is measuring an emergent property, much like a thermometer measures temperature without revealing the intricate dance of every individual molecule. It is a breathtaking idea, one that invites us to rethink not only physics, but our own place within the cosmos. In the next chapter, we will travel back to the birth of quantum theory itself, meeting the brilliant minds who unknowingly opened the door to this astonishing vision of reality. A universe where certainty dissolves into probability, where particles refuse to live independent lives, and where time itself may be one of nature's most beautiful illusions. When the quantum revolution began, at the dawn of the 20th century, physics appeared nearly complete. Many scientists believed that only a handful of small problems remained before humanity would possess a complete understanding of nature. Isaac Newton's laws had explained the motion of planets for more than 2 centuries. James Clerk Maxwell had united electricity, magnetism, and light into a single elegant theory. Steam engines, telegraphs, electric lights, and the first automobiles demonstrated the remarkable power of scientific knowledge. The universe seemed orderly, predictable, and beautifully mechanical. If someone knew the position and velocity of every object, it appeared possible, at least in principle, to calculate both the future and the past with unlimited precision. This idea became known as determinism. Pierre-Simon Laplace imagined an all-knowing intelligence, later called Laplace demon, that could predict every future event by knowing the exact state of the universe at one instant. To many physicists, the cosmos resembled an unimaginably sophisticated clock, each gear turning according to fixed mathematical laws. Then came an unexpected mystery. When scientists heated a piece of metal until it glowed, its color changed gradually from deep red to orange, then yellow, and finally brilliant white. This simple observation had been familiar for centuries, yet no existing theory could accurately explain the pattern of light being emitted. Classical physics predicted something absurd. According to its equations, hot objects should release an infinite amount of energy at ultraviolet wavelengths. This impossible prediction became known as the ultraviolet catastrophe. Clearly, nature was refusing to follow the rules scientists believed they understood so well. In 1900, the German physicist Max Planck proposed a mathematical solution that he considered little more than a convenient trick. He suggested that energy could not be emitted continuously. Instead, it came in tiny discrete packets. He called these packets quanta, from the Latin word meaning how much. Planck himself did not fully appreciate how revolutionary this idea would become. He simply wanted equations that matched experimental observations. Yet those tiny packets of energy quietly shattered centuries of classical thinking. 5 years later, a young patent clerk named Albert Einstein extended Planck's strange proposal even further. Light, Einstein suggested, sometimes behaved as though it consisted of individual particles, later called photons. His explanation solved another puzzle known as the photoelectric effect, in which light striking certain metals ejects electrons. No matter how bright red light became, it could never eject these electrons if its frequency remained too low. Meanwhile, even faint blue light could do so immediately. The discovery revealed something astonishing. The energy carried by light depended not on its brightness but on the energy of individual photons. For this work, Einstein would later receive the Nobel Prize, not for relativity, but for helping establish quantum theory. The surprises kept coming. In 1913, the Danish physicist Niels Bohr introduced a new model of the atom. Instead of electrons spiraling endlessly toward the nucleus, they occupied specific allowed orbits. They could jump between these orbits by absorbing or emitting photons with precisely defined energies. These quantum jumps seemed almost magical. An electron did not gradually move from one orbit to another. It simply appeared in a different state. No smooth transition. No visible journey. Nature, at its smallest scales, behaved in sudden leaps rather than continuous motion. During the following decade, the foundations of quantum mechanics rapidly expanded. Louis de Broglie proposed that matter itself possesses wave-like properties. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger introduced his famous wave equation. Paul Dirac united quantum mechanics with special relativity, predicting entirely new particles before experiments confirmed their existence. These scientists were not merely improving older theories. They were constructing an entirely new language for describing reality. One of the most profound discoveries emerged almost accidentally. The equations describing microscopic particles did not assign them definite positions or velocities until measurements were performed. Instead, they described a range of possible outcomes. This mathematical object became known as the wave function. The wave function does not resemble an ordinary ocean wave. Rather, it represents the probabilities of different measurement results. Before observation, an electron is not simply hiding at one unknown location waiting to be discovered. According to the standard interpretation, its measurable properties exist only as probabilities distributed across many possibilities. This idea remains one of the most debated aspects of quantum mechanics. Does measurement actually create physical reality? Or does it merely reveal one possibility among many? Even today, physicists continue exploring these questions through competing interpretations. Yet regardless of interpretation, the mathematics works with extraordinary precision. Its predictions have been confirmed to more than 10 decimal places in some experiments, making quantum electrodynamics one of the most accurate scientific theories ever developed. Still, many physicists found the philosophical implications deeply unsettling. Perhaps the most famous challenge came from Heisenberg himself. His uncertainty principle demonstrated that certain pairs of physical quantities, such as position and momentum, cannot both be known with unlimited precision at the same time. This limitation is not caused by poor instruments, nor does it arise from human ignorance. It is woven into the mathematical structure of nature. Imagine attempting to photograph a hummingbird in complete darkness. To illuminate it, you must shine light upon it, but the light itself disturbs the bird. At the quantum level, every measurement inevitably becomes part of the system being measured. The observer and the observed are no longer completely separate. Although this analogy captures only part of the story, it hints at why quantum reality differs so dramatically from everyday intuition. The deeper scientists looked, the less the universe resembled a machine. Instead, it appeared more like an intricate web of possibilities. Then another remarkable idea emerged. If particles could exist in combinations of multiple possible states before measurement, could two particles share one combined wave function even after traveling far apart? Schrödinger investigated precisely this question. His calculations showed that quantum systems could indeed become inseparable in a mathematical sense. The complete description belonged to the pair as a whole rather than to either particle individually. In 1935, Schrödinger introduced a new word for this astonishing phenomenon. He called it entanglement. He believed it was not an unusual feature of quantum mechanics, but its defining characteristic. According to Schrödinger, entanglement was the essential trait that distinguished the quantum world from classical physics. The implications were staggering. If two particles shared a single quantum state, then measuring one seemed to instantaneously determine the corresponding properties of the other, regardless of the distance between them. This conclusion deeply troubled Einstein. The same year, together with Boris Podolsky and Nathan Rosen, he published one of the most influential papers in the history of physics. Known today as the EPR paper, it argued that quantum mechanics must be incomplete. Einstein could not accept that nature allowed such mysterious connections across space. Surely, he believed, some deeper hidden reality remained undiscovered. For decades, the debate remained unresolved. Was quantum mechanics merely an incomplete approximation? Or was the universe genuinely stranger than anyone had dared imagine? The answer would require generations of increasingly sophisticated experiments, powerful lasers, ultrasensitive detectors, and brilliant theoretical insights. Those experiments would ultimately reveal that Schrödinger's extraordinary intuition had been remarkably close to the truth. Entanglement was not a mathematical illusion. It was one of the deepest organizing principles of the universe itself. And as physicists began to understand its extraordinary power, an even more radical possibility slowly emerged. Perhaps entanglement does not merely connect particles. Perhaps it also helps weave the very fabric of space and time. Einstein's greatest doubt. By the middle of the 1930s, quantum mechanics had become the most successful scientific theory ever developed for describing the microscopic world. Its equations predicted the behavior of atoms with astonishing accuracy. Chemists used it to explain the structure of molecules. Physicists applied it to understand the spectra of distant stars. Engineers were beginning to realize that the strange quantum rules would eventually lead to entirely new technologies. Yet despite its extraordinary success, one man remained unconvinced: Albert Einstein. This may seem surprising, since Einstein himself had helped launch the quantum revolution. His explanation of the photoelectric effect had shown that light behaves as discrete particles called photons. His work laid one of the essential foundations upon which quantum mechanics was built. But Einstein was searching for something deeper than successful equations. He wanted a description of reality itself. To Einstein, physics was not merely a collection of mathematical tools for predicting experiments. It was humanity's attempt to uncover the hidden architecture of nature. A scientific theory should describe what exists, whether or not anyone happens to observe it. Quantum mechanics appeared to challenge precisely that principle. According to the standard interpretation developed largely by Niels Bohr and Werner Heisenberg, physical properties such as position, momentum, or polarization do not always possess definite values before measurement. Instead, they are described by probabilities encoded within the wave function. Only when a measurement occurs does one specific outcome emerge. Bohr viewed this as a profound lesson about nature. Einstein viewed it as evidence that something essential was missing. One of Einstein's most famous remarks captures his discomfort perfectly. God does not play dice with the universe. Whether or not one agrees with his conclusion, the statement reveals his philosophy. He believed the universe operated according to precise underlying laws, even if humanity had not yet discovered them. Randomness, in his view, reflected incomplete knowledge rather than fundamental reality. Bohr answered just as memorably, "Einstein, stop telling God what to do." Although often quoted today with a smile, the disagreement between these two giants of science was remarkably serious. Their conversations stretched across decades, influencing generations of physicists. Each respected the other's brilliance. Neither succeeded in convincing the other. The heart of the disagreement became especially clear in 1935, when Einstein joined Boris Podolsky and Nathan Rosen to publish a paper that would become one of the most influential scientific articles ever written. Today, it is simply known as the EPR paper. Rather than claiming quantum mechanics was obviously wrong, Einstein and his colleagues proposed what scientists call a thought experiment. Thought experiments are among the most powerful tools in physics. Instead of performing laboratory measurements, they use careful logic to explore the consequences of existing theories. Einstein imagined two particles interacting briefly before flying far apart. According to quantum mechanics, the particles could become entangled. Suppose their total momentum must always equal zero. If one particle is later measured moving to the left, the other must be moving equally to the right. Likewise, if one particle's position becomes precisely known, the other's position is immediately constrained by the mathematics describing their shared state. Here came Einstein's question. Imagine the particles have traveled so far apart that even light would require years to travel between them. How can measuring one particle possibly influence the other instantaneously? There seemed to be only two possibilities. Either information somehow traveled faster than light, or both particles already possessed hidden properties before anyone measured them. The first possibility directly conflicted with Einstein's own theory of relativity, which states that no information can travel faster than the speed of light in a vacuum. The second possibility suggested that quantum mechanics was incomplete. Einstein strongly favored the second explanation. He believed hidden variables, unknown physical properties, must already determine every measurement outcome. Quantum theory, in his view, resembled a statistical description of something deeper, much as the temperature of a gas summarizes the motion of countless individual molecules. The probabilities reflected ignorance, not fundamental uncertainty. Many physicists found this reasoning persuasive. After all, everyday experience encourages precisely this intuition. Imagine placing two identical gloves into separate boxes. One box travels to New York. The other is shipped to Sydney. Months later, you open the first box and discover a left-hand glove. Instantly you know the second box contains the matching right-hand glove. No mysterious communication occurred. The answer was determined from the beginning. Einstein suspected entangled particles behaved in a similar way. Perhaps they carried hidden instructions all along. For decades, no experiment could distinguish Einstein's picture from the standard quantum interpretation. The debate remained philosophical. Then an unexpected breakthrough arrived from an unlikely direction. In 1964, a relatively little-known physicist named John Stuart Bell examined Einstein's challenge with extraordinary mathematical insight. Bell realized that hidden variable theories and genuine quantum mechanics do not merely tell different stories. They make measurably different predictions. His famous theorem transformed a philosophical debate into something laboratories could actually test. Bell derived mathematical inequalities that any local hidden variable theory must obey. Quantum mechanics predicted that under certain carefully designed experiments, these inequalities would be violated. The implications were revolutionary. For the first time, scientists possessed an experimental roadmap capable of deciding between Einstein's intuition and the quantum description. Initially, performing such experiments proved extraordinarily difficult. Creating entangled particles under controlled conditions required technologies that simply did not yet exist. Sensitive photon detectors were unreliable. Laser systems remained primitive. Experimental errors left room for doubt. Nevertheless, researchers continued improving their methods decade after decade. In the early 1970s, physicist John Clauser performed one of the first important Bell tests. The results favored quantum mechanics, although certain experimental loopholes remained. The most famous early experiments followed in the 1980s, led by Alain Aspect and his colleagues in France. Aspect designed ingenious systems that rapidly changed detector settings while entangled photons were already in flight, preventing the particles from somehow agreeing on outcomes beforehand. Again, Bell's inequalities were violated exactly as quantum mechanics predicted. Einstein's local hidden variable picture faced an increasingly difficult challenge. Yet science demands extraordinary caution. Physicists identified additional loopholes. Could inefficient detectors bias the results? Could subtle experimental imperfections explain the observations? Rather than declaring victory, researchers spent decades designing even more precise experiments. Finally, in 2015, several independent research groups performed what became known as loophole-free Bell tests. Using sophisticated technology, they simultaneously closed the major remaining experimental loopholes. Once again, nature sided with quantum mechanics. The universe behaved exactly as Bell's mathematics had anticipated. These achievements became so significant that the 2022 Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for groundbreaking experiments with entangled photons and for establishing the foundations of quantum information science. Einstein had been mistaken about local hidden variables. Yet in another sense, his skepticism accomplished something remarkable. By questioning quantum mechanics so relentlessly, he inspired generations of physicists to devise ever more ingenious experiments. His doubts ultimately strengthened the theory he hoped to replace. This is one of science's greatest strengths. Progress does not arise from blind agreement. It emerges through careful questioning, relentless testing, and a willingness to let evidence decide. Today, entanglement is no longer viewed as an obscure curiosity. It has become the foundation of quantum cryptography, quantum teleportation, quantum sensing, and quantum computing. Yet perhaps its greatest gift is not technological. It forces us to reconsider one of our oldest assumptions, that objects exist as entirely separate things, connected only through space and time. Instead, the quantum world suggests something far stranger. Perhaps relationships come first. Perhaps separation itself is an approximation. And if space can emerge from these invisible quantum relationships, then an even more astonishing question naturally follows. Could time itself emerge in exactly the same way? A universe woven from invisible connections. Imagine standing beneath a clear night sky far from any city lights. Above you stretches a tapestry of countless stars. To your eyes, each star appears isolated, separated from every other by vast oceans of darkness. Constellations seem like simple patterns drawn upon a distant celestial sphere, each point of light existing independently. Yet astronomy tells a different story. Every star belongs to a larger structure. They orbit within galaxies. Galaxies gather into clusters. Clusters form immense superclusters connected by long filaments of gas and dark matter, creating what cosmologists call the cosmic web. On the largest scales, the universe resembles an intricate network rather than a collection of isolated objects. Something remarkably similar may be true at the quantum level. Although particles often appear to be separate entities, modern physics increasingly suggests that relationships between them may be more fundamental than the particles themselves. This idea represents one of the most profound shifts in scientific thinking since the time of Newton. For centuries, physics treated objects as the primary ingredients of reality. A planet existed first. Its relationships with other planets came second. An atom existed first. Its interactions followed afterward. The universe resembled an enormous collection of tiny building blocks assembled into increasingly complicated structures. Quantum mechanics quietly challenged this picture. When two particles become entangled, describing either one independently becomes impossible. Their complete quantum state belongs to the pair as a whole. It is almost as though the universe refuses to assign each particle its own complete identity. Instead, identity itself becomes shared. To appreciate how extraordinary this is, imagine reading only every other page of a novel. The individual pages make little sense on their own. Characters appear without explanation. Conversations begin halfway through. Events seem disconnected. Only by reading the entire book do the pages reveal their true meaning. Entangled particles behave in a surprisingly similar way. Viewed separately, each particle appears incomplete. Together, however, they form a perfectly consistent description. The relationship contains information that neither particle possesses alone. Physicists refer to this as quantum correlation, but the word correlation can be misleading. In everyday life, correlations are familiar. Rain often accompanies dark clouds. Ice cream sales rise during summer. Longer nights coincide with colder temperatures. These are statistical relationships between events that already possess their own independent existence. Quantum entanglement is far deeper. The mathematical description of one particle cannot be cleanly separated from the description of the other. The relationship is not simply added afterward. It is built into the very structure of the wave function. This subtle distinction has enormous consequences. During the late 20th century, physicists began asking an astonishing question. If entanglement is so fundamental, could it actually give rise to something larger? Could the geometry of the universe itself emerge from quantum relationships? At first glance, the idea sounds almost impossible. After all, space seems obvious. You can stretch out your hand, walk across a room, measure the distance between two mountains. Surely space must exist before anything can occupy it. Yet history repeatedly reminds us that intuition evolved to help our ancestors survive on Earth's surface, not to understand the deepest layers of reality. Our senses did not evolve to perceive atoms. They cannot detect radio waves. They do not naturally reveal curved spacetime or quantum superposition. Again and again, science has shown that reality extends far beyond ordinary experience. One clue came from an unexpected source: black holes. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The resulting gravitational field becomes so intense that beyond a certain boundary, the event horizon, not even light can escape. For many years, physicists believed black holes simply swallowed everything forever. Then Stephen Hawking made a remarkable discovery. By combining quantum mechanics with relativity, he showed that black holes are not entirely black. They emit an extremely faint glow now known as Hawking radiation. This revelation created one of the greatest puzzles in theoretical physics. According to quantum mechanics, information should never be truly destroyed. Yet if a black hole eventually evaporates through Hawking radiation, what happens to all the information about the matter that once fell inside? This became known as the black hole information paradox. For decades, researchers searched for a solution. Their efforts led to an unexpected realization. The amount of information a black hole can contain appears proportional not to its volume, but to the surface area of its event horizon. This surprising relationship inspired the holographic principle. A familiar hologram stores three-dimensional information on a two-dimensional surface. Likewise, some physicists proposed that our seemingly three-dimensional universe might itself emerge from information encoded on a lower-dimensional boundary. Although still an active area of research, this idea has profoundly influenced modern theoretical physics. It suggests that space may not be fundamental after all. Instead, geometry itself could arise from deeper patterns of quantum information. One of the most influential developments came from Juan Maldaceno's proposal known as the ADS-CFT correspondence. Without diving into its challenging mathematics, the essential idea is breathtaking. Two completely different descriptions of reality, one involving gravity in a higher dimensional space, the other involving quantum fields on a lower dimensional boundary, can describe exactly the same physics. It is as though two entirely different languages tell the same story. In one language, gravity curves space. In the other, quantum interactions unfold without gravity. Both descriptions remain mathematically equivalent. This remarkable duality encouraged physicists to think differently about spacetime itself. Among those exploring these ideas were Mark van Ramsdonck and Leonard Susskind. Van Ramsdonck demonstrated mathematically that reducing quantum entanglement between different regions of space causes the geometry connecting them to weaken. Increase the entanglement, and the regions become more strongly connected. Decrease it enough, and space-time itself begins to fall apart. This result suggested something astonishing. Entanglement may act like the invisible stitching holding the fabric of space together. Susskind, working alongside Juan Maldaceno, later proposed an even bolder conjecture known by the memorable phrase ER equals EPR. The initials combine two famous ideas. ER refers to Einstein-Rosen bridges, commonly called wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox concerning entanglement. The conjecture suggests that every pair of entangled particles might be connected by an extremely tiny, non-traversable geometric bridge. Not a tunnel through which matter or information travels faster than light. Rather, a deep mathematical equivalence between geometry and entanglement. The idea remains speculative. No experiment has yet confirmed that microscopic wormholes literally connect entangled particles. Nevertheless, the conjecture has inspired an enormous amount of research because it hints at a profound unity between gravity and quantum mechanics. If these ideas prove correct, then something extraordinary follows. Space is not the stage upon which the universe performs. Space is part of the performance itself. Its geometry emerges from an unimaginably vast network of quantum relationships, woven together across every corner of reality. And if the dimensions through which we move can emerge from entanglement, then another question naturally becomes impossible to ignore. What about time? Could the steady flow from past to future also arise from hidden quantum connections? Could the ticking of every clock, the beating of every heart, and the unfolding of every memory be features of an emergent reality rather than properties of the universe at its deepest level? In the next chapter, we will explore this remarkable possibility, following physicists into a world where the distinction between past, present, and future begins to blur, and where time itself may be one of nature's most elegant creations rather than one of its fundamental ingredients. Does time really flow? Every morning, the world seems to begin again. The first rays of sunlight stretch across the horizon. Birds greet the dawn with familiar songs. Coffee grows warm in a cup, while the cool air of the night gradually fades. Children leave for school. Adults begin their work. Shadows move slowly across buildings until evening arrives once more. Everything about daily life reinforces one simple belief: time moves. It carries the universe from yesterday toward tomorrow with quiet, unstoppable determination. But one of the most surprising discoveries in modern physics is that the fundamental equations describing nature contain remarkably little evidence that time actually flows at all. This idea may sound almost impossible. After all, we do not simply believe that time passes, we experience it. Every memory belongs to the past. Every expectation points toward the future. We celebrate birthdays because we grow older. Ice melts. Flowers bloom. Mountains erode. Galaxies evolve. Surely these changes prove that time itself is flowing. Yet physics encourages us to separate two ideas that often appear identical. The first is change. The second is the passage of time. They are not necessarily the same thing. Imagine watching a beautifully illustrated flipbook. Each page contains a slightly different drawing. Flip through the pages quickly, and motion suddenly appears. A bird seems to fly across the sky. A flower opens. A waterfall tumbles down a mountain. Yet nothing inside the book is actually moving. Every page simply exists. Movement emerges because your mind experiences the pages in sequence. Some physicists have wondered whether reality might resemble this picture, not because the universe is literally a flipbook, but because what we call the flow of time could emerge from relationships among different physical states rather than from an invisible river carrying everything forward. One of the earliest hints came from Albert Einstein himself. After developing the theory of relativity, Einstein realized that different observers do not always agree on which events happen simultaneously. Suppose two lightning bolts strike opposite ends of a moving train. An observer standing on the railway platform might conclude that both strikes occurred at exactly the same moment. Meanwhile, a passenger riding inside the train could calculate that one strike occurred before the other. Neither observer is mistaken. Each measurement is correct within its own frame of reference. This realization overturned centuries of intuition. There is no universal cosmic clock synchronizing every event throughout the universe. Instead, time becomes intertwined with space to form a single four-dimensional structure known as spacetime. In this picture, every event occupies its own location within spacetime, rather like cities marked upon a map. The map itself does not flow. It simply exists. Some philosophers and physicists call this perspective the block universe. According to the block universe interpretation, the past, present, and future all exist within spacetime, much as different locations all exist simultaneously on Earth's surface. Yesterday is no longer. Tomorrow has not yet arrived. These statements describe human experience. They may not describe reality at its deepest level. Imagine opening a world atlas. Paris, Tokyo, Cairo, and Buenos Aires all appear together on different pages. No city comes into existence only after another disappears. They simply occupy different locations. Likewise, every moment of your life, from your earliest childhood memory to your final breath, might occupy different coordinates within spacetime. Your consciousness experiences them one after another, creating the familiar sensation that time flows. The universe itself, however, may simply contain the entire structure at once. Einstein hinted at this view after the death of his close friend Michel Besso. In a letter to Besso's family, Einstein wrote that for physicists who believe in relativity, the distinction between past, present, and future is only a stubbornly persistent illusion. He did not mean that time is unreal. He meant that our experience of its passage may not correspond to the universe's fundamental structure. Not every physicist accepts the block universe interpretation. Science remains open to several competing ideas. Nevertheless, relativity demonstrates beyond doubt that the present moment is not universal. Different observers moving differently through spacetime slice reality into different sets of simultaneous events. Already, the ordinary picture of a single shared now begins to dissolve. Quantum mechanics deepens the mystery. Its equations describe probabilities evolving according to mathematical rules that are largely reversible. If a quantum system evolves without interacting with its environment, the equations work equally well whether time moves forward or backward. In other words, the microscopic laws themselves often make almost no distinction between past and future. This raises an extraordinary question. If the deepest laws of physics are largely time-symmetric, why does everyday life possess such a strong direction? Why do eggs fall and break, but broken eggs never leap back together? Why does perfume spread across a room instead of gathering neatly back into its bottle? Why do we remember yesterday but not tomorrow? The answer appears to lie not in the laws themselves but in probability. Here enters one of the most important ideas in all of physics: entropy. Entropy is often described as a measure of disorder, although many physicists prefer to think of it as the number of microscopic arrangements compatible with a system's overall appearance. Imagine opening a brand new deck of playing cards. Fresh from the factory, every suit appears perfectly ordered. Shuffle the deck thoroughly. The cards become mixed into what appears to be random order. Could another series of random shuffles accidentally restore the original arrangement? Yes. But the probability is unimaginably small. There are vastly more disordered arrangements than ordered ones. Nature therefore tends toward increasing entropy, not because it is forced to, but because overwhelmingly more possibilities exist. This statistical tendency creates what scientists call the arrow of time. The arrow of time points from lower entropy toward higher entropy. A hot cup of tea cools because there are enormously more ways for energy to spread evenly through the room than to remain concentrated inside the cup. Smoke disperses because there are vastly more arrangements in which its molecules are scattered than gathered. Stars eventually exhaust their fuel because physical processes naturally move toward increasingly probable configurations. Notice something remarkable. None of these examples require time itself to flow. They require only sequences of physical states becoming statistically more probable. In this sense, what we experience as the direction of time may arise from the evolution of entropy rather than from an invisible temporal current. Some physicists have suggested an even deeper possibility. Perhaps time emerges whenever information becomes organized in a particular way. As quantum systems interact with their environments, information spreads through entanglement. Tiny quantum uncertainties become amplified into the familiar classical world we experience every day. The past becomes increasingly well-defined because records accumulate. Footprints remain in wet sand. Tree rings preserve seasons. Photographs capture moments. Neurons store memories. The future, by contrast, contains no such records. Perhaps that is why we remember one direction but not the other. Our experience of flowing time may be intimately connected to the growth of information throughout the universe. This idea remains an active area of research. Scientists continue exploring whether entropy, information, and quantum entanglement together create the arrow of time that structures every moment of our lives? If so, then clocks do not reveal a fundamental river flowing beneath reality. Instead, they measure the unfolding organization of an evolving quantum universe. And that leads to an even more profound question. If information and entanglement shape our experience of time, could they also explain why the present moment feels so uniquely real? In the next chapter, we will explore how memory, observation, and quantum information may work together to create the mysterious sensation we call now. The mystery of the present moment. There is a question so familiar that most of us rarely stop to ask it. What is happening now? The word now feels perfectly ordinary. It slips effortlessly into conversation. We promise to begin now. We remember what happened just now. We wonder what the future will bring, but we always imagine experiencing it as another present moment. The present seems to be the one place where reality truly exists. The past survives only in memory. The future appears only in imagination. Surely, we think, the present must be special. Yet modern physics offers an unexpected challenge. Despite centuries of scientific progress, no equation has ever identified a universal present moment shared by the entire cosmos. This absence is not an oversight. It is one of the deepest clues about the nature of reality. Imagine looking at Earth from the Moon. Light requires about 1.3 seconds to travel between the two worlds. When you see someone wave from Earth, you are not witnessing their present. You are seeing them as they were more than a second ago. Now imagine observing Earth from Mars. Depending on the planet's positions, the light reaching you may have spent anywhere from a few minutes to over 20 minutes crossing the solar system. Move farther still. Observe Earth from a planet orbiting a distant star 1,000 light-years away. The image arriving at your telescope left Earth when medieval civilizations were still flourishing. Every mountain, ocean, forest, and city you see belongs to Earth's distant past. The farther we look into space, the farther back in time we see. Astronomers often describe telescopes as time machines, not because they transport us through time, but because light itself requires time to travel. When the James Webb Space Telescope studies galaxies whose light has traveled for more than 13 billion years, it is observing the universe during its infancy, long before our Sun or Earth existed. This remarkable fact reveals something subtle. Different observers naturally possess different versions of what they call now. No signal can travel faster than light. Therefore, no observer can instantly know what is occurring everywhere else in the universe. The idea of a single cosmic present quietly dissolves. Einstein's theory of relativity formalized this insight through the relativity of simultaneity. Suppose two astronauts drift silently past one another in deep space, each traveling at a different velocity. Events that appear simultaneous to one astronaut may occur in a different order for the other. Neither observer is mistaken. The laws of physics guarantee that both descriptions remain equally valid. This is perhaps one of the strangest consequences of relativity. There is no privileged universal clock announcing the present throughout the cosmos. Every observer carries their own network of simultaneous events, determined by their motion through space-time. The present becomes local rather than universal. Yet our everyday experience tells a different story. We feel completely immersed in a moving present. Each moment seems to arrive, linger briefly, and then disappear forever. Where does this experience come from? Some neuroscientists believe the answer lies partly within the brain itself. Our nervous system never experiences the universe instantaneously. Light entering the eye requires time to trigger chemical reactions inside retinal cells. Electrical signals travel through the optic nerve before reaching the visual cortex. Sounds arrive through vibrating air molecules, activate delicate structures within the inner ear, and are processed by networks of neurons. Even the sensation of touch involves microscopic delays. Remarkably, your brain continuously combines all these slightly delayed signals into one seamless experience. The present you experience is not an infinitely thin instant. It is more like a carefully constructed window lasting a fraction of a second. Psychologists sometimes refer to this interval as the specious present. Although the name sounds unusual, the idea is simple. Your conscious awareness blends together a short duration into what feels like a single moment. Without this integration, conversation would become fragmented, music would dissolve into disconnected notes, and motion itself might appear as unrelated snapshots. Instead, the brain assembles countless incoming signals into a coherent experience that we naturally call now. This process resembles filmmaking in an unexpected way. A modern movie consists of 24 or more individual frames displayed every second. Each frame is perfectly still. Motion emerges only because the brain integrates them into continuous experience. Similarly, consciousness may weave together streams of sensory information into the flowing present we perceive. Of course, this analogy has limits. The universe is not necessarily composed of discrete frames. Time may remain continuous, or it may possess a structure far beyond anything currently understood. Still, the comparison illustrates an important point. Our experience of the present depends not only on physics but also on biology. Yet quantum theory introduces another fascinating possibility. Some physicists have proposed that the present becomes meaningful when quantum possibilities transform into definite outcomes. Before measurement, a quantum system may exist in a superposition, a mathematical combination of multiple possible states. After interaction with its environment, one stable outcome becomes part of the classical world. This process is often described using the concept of decoherence. Decoherence does not necessarily explain every aspect of measurement, nor does it magically solve every interpretational puzzle. Instead, it describes how delicate quantum relationships become dispersed into the surrounding environment. Imagine placing a single drop of blue ink into a clear glass of water. At first, the drop remains compact and easily recognizable. Gradually, it spreads outward until its molecules become mixed throughout the entire glass. Recovering the original drop becomes practically impossible. Quantum coherence behaves in a surprisingly similar fashion. A carefully prepared quantum state interacts with countless surrounding particles, air molecules, photons, vibrating atoms, and rapidly becomes entangled with its environment. The original quantum information does not simply disappear. Instead, it becomes distributed among unimaginably many microscopic degrees of freedom. The result is the stable classical reality we observe every day. A coffee cup remains on the table. A tree stands firmly in the garden. The moon follows its orbit around Earth. Quantum uncertainty still exists beneath the surface, but large-scale objects behave in wonderfully predictable ways. Some researchers suspect that our familiar experience of the present emerges during this continuous transition from quantum possibilities to stable classical records. Every interaction leaves traces. Photons scatter from surfaces. Atoms exchange energy. Neurons strengthen connections. The universe continually creates new records of itself. Perhaps what we call the present is not a moving point in time, but the ever-growing boundary where information becomes permanently embedded within reality. This picture beautifully connects physics with memory. Consider your own childhood. Those moments no longer exist as immediate experiences, yet traces remain. Photographs preserve birthdays. Letters preserve handwriting. Old buildings preserve craftsmanship. Most importantly, your brain preserves memories through intricate patterns of neural connections. The past feels fixed precisely because countless records point toward it. The future possesses no comparable archive. No photographs arrive from tomorrow. No fossils form before creatures live. No memories appear before experiences occur. In this sense, the distinction between past and future may arise because information accumulates in only one direction. The present becomes the frontier where new records are constantly being written. This idea remains speculative, but it resonates with several active areas of research involving quantum information, entropy, and the foundations of statistical mechanics. It reminds us that reality may be shaped as much by information as by matter and energy. Every atom carries information. Every photon carries information. Every interaction reshapes the information woven throughout the universe. And perhaps, hidden beneath these countless exchanges, quantum entanglement quietly knits together not only space, but our very experience of the passage from one moment to the next. In the next chapter, we will journey deeper into the world of quantum information itself, discovering why many physicists now believe that information, not particles, may be the most fundamental ingredient of reality, and how that astonishing idea could transform our understanding of both entanglement and time. Is information the true fabric of reality? For thousands of years, humanity has asked a remarkably simple question. What is everything made of? The ancient Greeks imagined that all matter arose from four basic elements: earth, water, air, and fire. Other civilizations proposed different combinations, seeking the smallest ingredients from which the visible world was built. Centuries later, chemistry revealed that matter consists of atoms. Then physicists discovered that atoms themselves contain electrons orbiting compact nuclei. Those nuclei, in turn, are composed of protons and neutrons. Eventually, even these particles were found to be built from more fundamental constituents known as quarks, held together by particles called gluons. Each generation believed it had reached nature's deepest layer. Each generation discovered another one waiting beneath. Today, a growing number of physicists are asking an even more surprising question. What if matter is not the most fundamental ingredient of reality at all? What if the universe is built from information? At first glance, this idea sounds almost philosophical. After all, information seems abstract. A sentence written on paper contains information. A melody stored inside a computer contains information. The sequence of letters within a book contains information. But physics uses the word in a much more precise way. Information describes the physical state of a system. Every atom carries information about its energy, momentum, electric charge, spin, and countless other measurable properties. Every photon traveling through space carries information about its wavelength, polarization, direction, and quantum state. Even empty space is not truly empty. According to quantum field theory, what we call the vacuum contains fluctuating quantum fields whose temporary excitations continuously appear and disappear. These fluctuations also carry information. From this perspective, the universe resembles an unimaginably vast network of information constantly changing, interacting, and reorganizing itself. One of the scientists who helped popularize this viewpoint was the American physicist John Archibald Wheeler. Wheeler had already contributed enormously to relativity, black hole physics, and nuclear science. It was he who coined the term black hole, a name now recognized around the world. Late in his career, Wheeler proposed an unforgettable phrase: "It from bit." The statement was wonderfully short but extraordinarily profound. By it, Wheeler meant that every physical object, every particle, every field, every galaxy, perhaps even spacetime itself, might ultimately arise from elementary units of information. He did not suggest that the universe is literally a computer. Instead, he argued that information may occupy a deeper level than matter itself. The idea inspired generations of researchers. As computers became increasingly powerful, physicists noticed remarkable similarities between quantum mechanics and information processing. Unlike ordinary computer bits, which can store either 0 or 1, quantum bits, known as qubits, can exist in superpositions of both possibilities simultaneously. More importantly, qubits can become entangled. This changes everything. Imagine reading a single page torn from a novel. You understand only fragments. Now imagine reading every page in its proper order. Meaning suddenly emerges. Similarly, individual qubits often contain surprisingly little useful information by themselves. Their true power lies in the relationships they share with other qubits. Entanglement allows information to be distributed across an entire quantum system rather than stored inside isolated components. This feature makes quantum information fundamentally different from classical information. A classical photograph can be divided into smaller pieces. Each fragment still contains part of the image. Quantum information behaves differently. Sometimes the complete information exists only within the correlations linking multiple particles together. Destroy those relationships, and the information itself becomes inaccessible. In this sense, the connections matter just as much as the objects being connected. Perhaps even more. This realization has transformed theoretical physics. Researchers studying black holes discovered that information plays a central role in understanding gravity itself. When Stephen Hawking first proposed that black holes slowly evaporate through quantum radiation, he believed the information describing everything that had fallen into the black hole might disappear forever. This conclusion deeply troubled physicists. Quantum mechanics insists that information is preserved. Destroying it would undermine one of the theory's most fundamental principles. The resulting debate lasted nearly 50 years. Some of the greatest minds in modern science searched for a solution. Eventually, the consensus gradually shifted. Most physicists now believe that information is indeed preserved, although exactly how remains an active area of research. This conclusion dramatically elevated the importance of information within fundamental physics. If information cannot truly disappear, perhaps it represents something even more basic than matter or energy. Quantum computing offers another remarkable illustration. A classical computer performs calculations by manipulating billions of tiny switches that are either on or off. Quantum computers operate according to entirely different principles. They manipulate superposition and entanglement, allowing enormous numbers of possible computational pathways to coexist during certain calculations. This does not mean quantum computers try every answer simultaneously, as they are sometimes described in popular media. The reality is subtler and even more fascinating. Quantum algorithms carefully orchestrate interference between probability amplitudes, strengthening correct solutions while cancelling incorrect ones. The result is a new kind of computation that exploits the mathematical structure of quantum information itself. Although practical quantum computers remain in their early stages, they already demonstrate that information behaves according to rules far richer than classical intuition suggests. Yet perhaps the most breathtaking development comes from an unexpected connection between information and geometry. Several modern theories indicate that the amount of entanglement between quantum systems determines the shape of spacetime itself. Imagine constructing a city entirely from roads. At first, there are only isolated villages. As more roads connect them, neighborhoods emerge. Eventually, a complex metropolis appears. Notice that the city is defined not only by its buildings but by the network of connections joining them. Some physicists suspect spacetime may emerge in a remarkably similar fashion. The roads are quantum entanglement. The city is the geometry of the universe. Increase the entanglement, and spacetime becomes smoothly connected. Reduce it, and geometry begins to fragment. This astonishing possibility has led some researchers to describe entanglement as the glue of spacetime. Not literal glue, of course. Rather, the mathematical relationships responsible for the universe's continuous structure. If this picture proves correct, it changes the way we think about existence itself. Matter would no longer occupy center stage. Information would. Particles would become excitations of quantum fields. Fields would be described through quantum information. Space would emerge from patterns of entanglement. Time might emerge from evolving informational relationships. Reality would become less like a machine built from tiny objects and more like a magnificent symphony composed of relationships. Each note gains meaning only because of the notes surrounding it. Remove every relationship, and music disappears. Keep the relationships, and harmony emerges. The same may be true of the cosmos. Galaxies, stars, planets, atoms, and people may all be expressions of one vast informational structure whose deepest language is written not in matter alone, but in connections. This perspective also changes how we view ourselves. Every memory stored within your brain is information. Every thought arises from patterns of electrical activity carrying information between billions of neurons. Every word you read at this very moment reshapes tiny networks of synaptic connections. Life itself depends upon the storage, transmission, and transformation of information. DNA preserves genetic information across generations. Cells constantly exchange chemical messages. The immune system identifies invading organisms by processing molecular information with astonishing precision. Nature, from the smallest bacterium to the largest galaxy cluster, appears to thrive on information. Perhaps this is not a coincidence. Perhaps information is the thread connecting every layer of reality. And if information lies beneath matter, and entanglement organizes information into coherent structures, then another remarkable question naturally arises. Where does consciousness fit into this extraordinary picture? Could our awareness of time itself emerge from the way information is processed within the brain? Or is consciousness simply another beautiful pattern woven into the universe's vast network of quantum relationships? In the next chapter, we will explore one of the most intriguing intersections of modern science, the relationship between quantum physics, consciousness, and our perception of reality, and discover why separating established science from fascinating speculation is just as important as asking bold questions in the first place. Consciousness, quantum reality, and the experience of time. Few questions have fascinated humanity more than the mystery of consciousness. Long before telescopes revealed distant galaxies or microscopes uncovered the hidden world of cells, people wondered about the nature of awareness itself. What allows us to experience the color of a sunset, the sound of falling rain, or the quiet feeling of remembering a childhood afternoon? Why does the universe not simply exist, but seem to be experienced from the inside? Science has made extraordinary progress in understanding the brain. Modern neuroscience has mapped regions responsible for language, vision, memory, movement, and emotion. Tiny electrical impulses race through networks of roughly 86 billion neurons. Each neuron forms thousands of connections, creating one of the most intricate structures known in the observable universe. Every second, trillions of signals pass through this astonishing biological network. And yet one great mystery remains. How do these physical processes give rise to subjective experience? Physicists sometimes call this question the measurement problem's philosophical cousin. Both ask how one kind of reality gives rise to another. In quantum mechanics, we ask how definite outcomes emerge from probabilities. In neuroscience, we ask how conscious experience emerges from physical processes inside the brain. The two mysteries appear similar. Whether they are actually connected remains one of the most debated questions in modern science. It is important to begin with a careful distinction. There is currently no accepted scientific evidence that consciousness causes the collapse of the quantum wave function or directly controls quantum events. Although this idea appears frequently in popular books, documentaries, and internet discussions, it is not the consensus view among physicists. Nevertheless, several intriguing hypotheses have explored possible relationships between quantum mechanics and consciousness. These ideas deserve attention, not because they have been proven, but because they encourage scientists to examine fundamental assumptions with great care. One of the earliest misconceptions arose from the language used to describe quantum measurements. Textbooks often state that a particle exists in multiple possible states until it is observed. Outside physics, the word observed usually implies a conscious person watching something happen. Within quantum mechanics, however, observation has a much broader meaning. A photon striking a detector counts as an observation. An electron interacting with an atom counts as an observation. Even collisions with molecules in the surrounding air can serve as measurements through the process of decoherence. Nature does not appear to wait for human eyes. Physical interactions occur continuously throughout the universe. Stars emitted light billions of years before conscious life existed on Earth. Galaxies formed. Atoms combined. Planets cooled. Supernovae exploded. Quantum processes unfolded long before any observer was present to witness them. This realization has led most physicists to conclude that consciousness is not required for ordinary quantum measurements. Still, consciousness remains profoundly mysterious. Some researchers have wondered whether quantum effects might nevertheless play a subtle role inside the brain. Perhaps the most widely discussed proposal came from the mathematical physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff. Together, they developed the OR hypothesis, short for orchestrated objective reduction. According to this speculative model, tiny structures inside neurons called microtubules might support quantum processes that contribute to conscious experience. Microtubules are real biological components. They help maintain the shape of cells, transport materials, and assist during cell division. Whether they also sustain meaningful quantum coherence long enough to influence cognition remains highly controversial. Many neuroscientists argue that the warm, wet environment of the brain causes quantum states to decohere far too quickly. Others continue investigating whether certain biological systems can preserve delicate quantum behavior under surprisingly ordinary conditions. Nature has already offered several remarkable examples. Photosynthetic organisms appear to exploit quantum coherence to improve the efficiency of energy transfer during photosynthesis. Certain migratory birds may use quantum processes within specialized proteins called cryptochromes to help detect Earth's magnetic field during navigation. Even some chemical reactions involving smell and enzyme activity have been examined for possible quantum contributions. These discoveries demonstrate that biology and quantum mechanics are not strangers. Life has evolved within the quantum world from the very beginning. Whether consciousness itself depends upon uniquely quantum mechanisms, however, remains unanswered. Regardless of the outcome, the question has inspired valuable research at the boundary between physics, biology, and neuroscience. Meanwhile, another line of inquiry asks a different question altogether. Perhaps consciousness does not require quantum mechanics in any special sense. Perhaps it emerges naturally from sufficiently complex information processing. According to this perspective, awareness arises when enormous networks of interacting neurons continuously integrate sensory information, memories, predictions, and emotions into a unified model of the world. Time plays an essential role in this process. Your brain is constantly predicting what will happen next. As you read these words, neural circuits anticipate the upcoming letters and sentences. When listening to music, your mind expects the next note before it arrives. While catching a ball, your brain calculates its future position almost automatically. Conscious experience is therefore deeply intertwined with prediction. Some neuroscientists have suggested that our perception of flowing time emerges because the brain continually compares incoming information with stored memories while simultaneously forecasting future events. The present becomes a dynamic bridge linking what has already occurred with what is about to happen. Notice how naturally this connects to quantum information. The universe records information through physical interactions. Your brain records information through changing neural connections. Both systems evolve continuously, creating new relationships while preserving traces of earlier states. Memory itself provides an illuminating example. Contrary to popular belief, memories are not stored like videos inside the brain. Each recollection reconstructs an event by activating distributed networks of neurons. Every time you remember something, the memory becomes briefly flexible before being stored again, often with tiny modifications. Your remembered past is therefore not a perfect archive. It is a continually updated reconstruction. This remarkable feature reminds us that subjective time differs from physical time. A joyful afternoon may seem to vanish in minutes. An anxious hour can feel endless. A familiar drive home may leave almost no conscious memories because the brain processed much of the journey automatically. Meanwhile, an exciting new experience fills memory with rich details, making the same amount of clock time seem much longer in retrospect. The brain does not measure time like an atomic clock. It measures significance, novelty, attention, and change. In this sense, each of us carries two different clocks. One is the physical clock governed by the laws of nature. The other is the psychological clock shaped by consciousness itself. These clocks usually remain synchronized well enough for everyday life. Yet they reveal that our experience of time depends not only on the structure of the universe but also on the structure of the mind experiencing it. This realization leads to a profound insight. Perhaps the greatest illusion is not that time exists. Rather, it is that our personal experience of time perfectly reflects the universe's deepest architecture. Physics suggests that spacetime may emerge from quantum relationships. Neuroscience suggests that the flowing present emerges from information processing inside the brain. Together, these perspectives paint a picture both humbling and beautiful. Reality may be far richer than either discipline can describe alone. As we continue our journey, one final mystery begins to appear on the horizon. If entanglement connects particles across enormous distances, and if space-time itself may emerge from quantum information, then could the entire universe be understood as one immense quantum system? In the next chapter, we will explore this breathtaking possibility, traveling from individual particles to the largest structures in existence, where cosmology and quantum mechanics begin to tell the same extraordinary story. The entangled cosmos. On the clearest nights, when the moon has not yet risen and the air is still, the sky reveals a breathtaking truth. Thousands of stars become visible to the naked eye. Stretching across the darkness is the pale ribbon of the Milky Way, a galaxy so immense that its light has traveled tens of thousands of years before reaching Earth. Beyond it lie countless other galaxies, many too faint for our eyes to detect. Each contains billions or even trillions of stars, and together they form a universe so vast that ordinary language struggles to describe its scale. Yet despite these unimaginable distances, many physicists have begun asking an astonishing question. Could the entire universe be connected by quantum entanglement? At first, the idea seems impossible. Entanglement is usually demonstrated with tiny particles inside carefully controlled laboratories. Researchers cool atoms to temperatures only fractions of a degree above absolute zero. They isolate photons from environmental disturbances and use exquisitely precise instruments to preserve delicate quantum states. The universe, by contrast, appears noisy and chaotic. Stars explode. Galaxies collide. Black holes consume matter. Radiation fills space. Surely quantum coherence could not survive amid such cosmic violence. Surprisingly, the story is more subtle. To understand why, we must journey back nearly 13.8 billion years to the earliest moments after the Big Bang. According to the standard cosmological model, the observable universe began in an unimaginably hot, dense state. Temperatures exceeded anything that can currently be reproduced in laboratories. Matter as we know it did not yet exist. Even atomic nuclei had not formed. Instead, the universe consisted of an extraordinarily energetic sea of quantum fields. Every particle that would one day become part of galaxies, planets, oceans, trees, and living beings existed only as excitations within these fundamental fields. During this earliest era, everything was astonishingly close together. Regions of space that are now separated by billions of light-years once occupied neighboring locations within the infant universe. This fact has profound implications. If quantum systems naturally become entangled through interaction, then the early universe likely contained enormous amounts of entanglement. As cosmic expansion stretched space itself, many of these primordial quantum relationships may have been carried outward across immense distances. Although decoherence transformed much of this quantum behavior into the familiar classical universe we observe today, traces of those earliest fluctuations remain. One of the greatest discoveries in modern astronomy provides remarkable evidence. In 1965, Arno Penzias and Robert Wilson accidentally detected a faint microwave signal arriving uniformly from every direction in the sky. At first, they suspected faulty equipment. They even cleaned pigeon droppings from their radio antenna, believing they had found the source of the mysterious noise. But the signal remained. It turned out to be one of the most important observations in scientific history. Today we know it as the cosmic microwave background, often abbreviated as the CMB. This ancient radiation began its journey approximately 380,000 years after the Big Bang, when the expanding universe cooled enough for atoms to form and light could finally travel freely through space. The CMB is often described as the oldest light in the observable universe. Its temperature is astonishingly uniform, about 2.725 degrees above absolute zero. Yet tiny variations exist. These minute fluctuations, measured to accuracies of millionths of a degree, reveal the seeds from which every galaxy eventually grew. Where did these tiny irregularities originate? Modern cosmology points toward quantum mechanics. According to the leading theory of cosmic inflation, the infant universe underwent an incredibly rapid expansion during an unimaginably brief fraction of a second. Quantum fluctuations that normally exist only on microscopic scales were stretched across astronomical distances. These tiny fluctuations later became regions slightly denser than their surroundings. Gravity gradually amplified these differences over billions of years, eventually producing galaxies, stars, and planets. In an extraordinary sense, every galaxy in the night sky owes its existence to quantum events that occurred when the universe was unimaginably young. The largest structures in existence may therefore have originated from the smallest fluctuations nature allows. This remarkable connection links quantum physics directly to cosmology. The universe did not simply evolve according to quantum laws. Its very structure may have been shaped by them. Researchers have begun exploring whether remnants of primordial quantum entanglement could still influence the large-scale universe today. These investigations remain highly speculative, and no definitive evidence has yet confirmed such long-range entanglement across cosmic scales. Nevertheless, the possibility has inspired exciting new research. Some cosmologists study whether quantum correlations could leave subtle signatures within the cosmic microwave background. Others investigate whether inflation naturally produces entangled regions whose effects might someday become observable. Still others seek a deeper theory uniting quantum mechanics with gravity, hoping it will reveal how space-time itself emerged from quantum information during the universe's earliest moments. One particularly fascinating idea involves the wave function of the universe. In ordinary quantum mechanics, every isolated system possesses a wave function describing its possible states. But what happens when the system includes everything? There is no outside observer, no external measuring device, no environment beyond the universe itself. This challenge inspired physicists Bryce DeWitt and John Wheeler to develop what became known as the Wheeler-DeWitt equation. Unlike most familiar equations in physics, it contains no explicit time variable. In a surprising sense, the equation describing the quantum state of the entire universe appears timeless. This discovery startled many researchers. How can a timeless equation describe a universe filled with clocks, motion, history, and evolution? One possibility is that time emerges only within subsystems of the universe. Observers like ourselves experience change because we are part of the system rather than external to it. Different parts of the universal wave function evolve relative to one another, creating the appearance of temporal flow. From the perspective of the universe as a whole, however, there may be no single cosmic clock. This idea echoes themes we encountered earlier. Perhaps time is not fundamental. Perhaps it emerges from relationships. If so, then the history of the cosmos resembles a magnificent symphony. No individual note contains the entire composition. Only the relationships among notes create melody, rhythm, and harmony. Likewise, no single particle contains the universe. Its richness emerges from countless interactions woven together through quantum information. Some theoretical physicists have suggested that every interaction leaves an informational thread linking different regions of reality. Most of these threads become hidden beneath decoherence, making the classical world appear local and independent. Yet beneath that familiar surface, quantum theory hints at a deeper unity. Not a mystical unity, but a mathematical one. A unity described by correlations, information, and entanglement. It is a picture of the universe that is simultaneously elegant and humbling. Every atom in your body was forged inside ancient stars. The calcium in your bones, the oxygen you breathe, the iron in your blood, and the carbon that forms every living cell were created through nuclear reactions billions of years ago. Long before Earth existed, these atoms traveled through interstellar space before becoming part of new stars, planets, and eventually living organisms. In that sense, every person carries within them a tangible record of cosmic history. We are not separate from the universe. We are one of the ways the universe has organized itself. Whether quantum entanglement extends meaningfully across the largest cosmic scales remains an open scientific question. Future observations, more powerful telescopes, and new theories may eventually provide answers. But even now, one conclusion is difficult to ignore. The universe is not merely a collection of isolated objects scattered through empty space. It is an evolving network of relationships, stretching from the smallest quantum fluctuations to the largest clusters of galaxies. And hidden within those relationships may lie the final clue to understanding one of nature's greatest mysteries. If time emerges from quantum information, if space emerges from entanglement, and if the universe itself can be described as a single quantum system, then what does this reveal about reality itself? In the next chapter, we will explore how physicists are attempting to unite quantum mechanics and gravity into one coherent theory, a quest that may finally explain why space, time, and entanglement appear so deeply intertwined. The search for a theory beyond time. Throughout the history of science, there have been rare moments when two successful ideas refused to fit together. For centuries, astronomers carefully measured the motions of planets while physicists studied the forces acting upon objects here on Earth. Isaac Newton united these seemingly separate worlds into a single theory of gravity. Suddenly, the falling of an apple and the orbit of the moon became different expressions of the same natural law. More than 200 years later, James Clerk Maxwell achieved another remarkable unification. Electricity, magnetism, and light, once considered entirely different phenomena, became parts of one elegant mathematical framework. These breakthroughs transformed our understanding of reality. Today, physics stands before another great challenge. The universe is governed by two extraordinarily successful theories. One describes the very large. The other describes the unimaginably small. Both have passed every experimental test placed before them. And yet, they refuse to coexist peacefully. The first theory is Einstein's general theory of relativity. Published in 1915, it replaced Newton's concept of gravity with something far more beautiful. Instead of treating gravity as an invisible force pulling objects toward one another, Einstein proposed that matter and energy curve spacetime itself. Imagine placing a heavy bowling ball onto the center of a stretched rubber sheet. The surface bends downward. Now roll a marble across the sheet. Rather than traveling in a straight line, the marble follows the curved surface created by the heavier object. Although this familiar demonstration is only an analogy, it cannot fully capture four-dimensional curved spacetime. It provides an intuitive glimpse into Einstein's extraordinary insight. Planets orbit stars not because they are pulled through space by mysterious forces. They move along the natural curves created by spacetime itself. General relativity has been spectacularly successful. It correctly predicts the bending of light around massive objects, the expansion of the universe, the behavior of neutron stars, and the existence of black holes. In 2015, scientists directly detected gravitational waves, tiny ripples traveling through spacetime itself, exactly 100 years after Einstein predicted them. The discovery marked one of the greatest achievements in modern astronomy. Meanwhile, another theory was revolutionizing our understanding of matter. Quantum mechanics revealed that particles behave as probability waves. Fields fluctuate continuously. Entanglement links distant systems. Uncertainty becomes fundamental. Combined with special relativity, quantum mechanics evolved into quantum field theory, the framework underlying the standard model of particle physics. This remarkable theory describes electrons, quarks, neutrinos, photons, gluons, and the Higgs boson with astonishing precision. Nearly every experiment performed in high-energy particle accelerators confirms its predictions. Yet a problem appears whenever these two magnificent theories meet. Imagine shrinking your attention towards smaller and smaller distances. At ordinary scales, gravity is extremely weak. A small refrigerator magnet can easily overcome the gravitational pull of the entire Earth when lifting a paperclip. But at unimaginably tiny distances, around the Planck length, approximately 1.6 times 10 cubed meters, gravity is expected to become as strong as the other fundamental forces. At this scale, the smooth spacetime described by general relativity may no longer exist. Instead, quantum fluctuations become so violent that spacetime itself may begin fluctuating. John Wheeler described this hypothetical realm as quantum foam. Picture the surface of a calm lake viewed from high above. It appears perfectly smooth. Fly lower. Small ripples become visible. Closer still, individual waves dominate the landscape. Now imagine approaching reality itself with increasing magnification. Eventually, the apparently smooth fabric of spacetime might reveal a restless microscopic structure filled with constantly changing geometries. Tiny wormholes could appear and disappear. Space might fluctuate. Even the distinction between here and there could lose its familiar meaning. No experiment has yet observed quantum foam directly. The scale is so unimaginably small that current technology cannot probe it. Nevertheless, nearly every candidate theory of quantum gravity predicts that classical spacetime eventually gives way to something fundamentally different. This realization has inspired several ambitious approaches. One of the oldest is string theory. Instead of treating elementary particles as point-like objects with no internal size, string theory proposes that they are tiny vibrating strings. Each vibrational pattern corresponds to a different particle. An electron is one vibration. A photon is another. A graviton, the hypothetical quantum particle of gravity, would be yet another. Just as different notes emerge from the same violin string vibrating in different ways, all particles might arise from one fundamental ingredient. To remain mathematically consistent, most versions of string theory require additional spatial dimensions beyond the familiar three. These extra dimensions would be extraordinarily small, curled into complex geometric shapes invisible at everyday scales. Although direct experimental evidence for string theory remains absent, its mathematical richness has produced many profound insights, including surprising connections between gravity, black holes, and quantum information. Another influential approach is loop quantum gravity. Rather than replacing particles with strings, this theory suggests that spacetime itself possesses an atomic structure. According to this picture, space is woven from tiny quantum loops forming an intricate network called a spin network. Distances and areas would no longer vary continuously. Instead, they would come in extremely small discrete units, much like matter consists of individual atoms rather than continuous substance. If this idea is correct, space itself resembles an extraordinarily fine fabric woven from quantum threads. Remarkably, time may also become discrete at these scales. The smooth flow we experience could emerge from countless microscopic quantum events, much as a flowing river emerges from the collective motion of countless water molecules. Other researchers pursue entirely different directions. Causal set theory proposes that spacetime consists not of continuous geometry but of discrete events linked by cause and effect relationships. In this picture, causality comes first. Geometry emerges afterward. Still others investigate approaches based on quantum information, tensor networks, or holographic principles, each suggesting that relationships, not objects, occupy the deepest layer of reality. Although these theories differ significantly, they share a remarkable theme. Space and time may not be fundamental ingredients of the universe. Instead, they emerge from deeper quantum structures. This represents a profound reversal of centuries of thinking. For Newton, space and time formed the stage upon which reality unfolded. For Einstein, the stage itself became dynamic. For today's quantum gravity researchers, even the stage may emerge from something more fundamental. Perhaps reality resembles a magnificent tapestry. From a distance, the fabric appears perfectly smooth. Move closer, and individual threads become visible. Closer still, each thread reveals countless intertwined fibers. Eventually, what seemed like continuous cloth resolves into an intricate pattern of relationships. The tapestry never stopped existing. Only our perspective changed. Perhaps spacetime behaves in exactly this way. Our everyday experience reveals only its large-scale appearance. Beneath that familiar surface lies a quantum architecture whose true nature we are only beginning to glimpse. One clue appears repeatedly across nearly every modern approach. Information. Whether through strings, loops, quantum fields, holography, or entanglement, information seems impossible to remove from the deepest equations. It appears again and again, quietly suggesting that reality is less about objects moving through space and more about patterns of relationships evolving within an informational universe. If this vision proves correct, then one of the oldest questions in philosophy returns with new scientific significance. What is truly fundamental? Matter, energy, space, time, or information itself? No one yet knows. Science has not reached its final theory. The search continues in laboratories, observatories, supercomputers, and chalk-covered offices around the world. Each new experiment brings another piece of the puzzle. Each new equation reveals another glimpse of the hidden architecture beneath reality. And perhaps the greatest surprise of all is this. The closer we look, the less the universe resembles a machine built from separate parts. Instead, it begins to resemble an immense web of relationships, a cosmos in which entanglement, information, space, and time are not independent ideas but different expressions of one deeper and more elegant truth. In the next chapter, we will leave the frontier of theoretical physics and reflect on what these discoveries mean for our understanding of existence itself, exploring how the illusion of time changes the way we think about memory, identity, and our place within the universe. Living in a timeless universe. Imagine that you are holding an old family photo. Perhaps it shows smiling faces gathered around a birthday cake, children running across a summer field, or grandparents sitting quietly in the evening light. The people in the photograph cannot see you. They do not know what will happen tomorrow. To them, that captured instant is simply the present. Yet as you look at the picture, you know an entire story that stretches far beyond its edges. You know what came before. You know what came after. You know how the children grew into adults, how seasons changed, how lives unfolded through years and decades. The photograph itself has not changed. Only your perspective has. Some physicists believe the universe may be understood in a surprisingly similar way. Rather than imagining reality as something continuously being created moment by moment, they suggest that the entire history of the cosmos may already exist as a single four-dimensional structure. Every event, from the birth of the first stars to the formation of Earth, from the first living cells to the final heartbeat of every person who has ever lived, occupies its own place within space-time. Nothing needs to move from the future into the present. Nothing needs to disappear into the past. Instead, every event simply exists within the geometry of the universe. This perspective is often called the block universe. It does not claim that change is unreal. Planets still orbit stars. Leaves still fall from trees. Children still become adults. Instead, it suggests that change is something experienced from within spacetime rather than something occurring to spacetime itself. Imagine reading a novel. Every chapter has already been printed before you open the book. The ending exists even while you are reading the first page. Yet your experience unfolds chapter by chapter. The story remains suspenseful because you do not yet know what lies ahead. Your journey through the book gives rise to the feeling of progression. Many physicists use this analogy carefully because it captures an important distinction. The existence of later chapters does not diminish the meaning of earlier ones, nor does it remove the emotional impact of discovery. Likewise, if the universe resembles a completed space-time structure, our experience of living through it remains entirely genuine. We still make decisions. We still learn. We still experience surprise, joy, grief, curiosity, and love. The fact that space-time may possess a larger structure does not erase human experience. It simply places that experience within a broader framework. This idea naturally raises one of philosophy's oldest questions. If the future already exists, do we truly possess free will? Scientists and philosophers continue debating this issue. Some argue that the block universe implies a deterministic cosmos in which every event is fixed. Others point out that quantum mechanics introduces genuine probabilities into physical law. Still others suggest that free will and determinism may not be opposites at all. Instead, they may describe reality from different perspectives. From inside the universe, choices remain real because they are part of the unfolding physical process. From outside the hypothetical block, those same choices simply occupy their own locations within space-time. No experiment has yet resolved this philosophical question. Physics describes what nature does remarkably well. Whether that description settles the meaning of choice remains an open conversation between science and philosophy. Another fascinating consequence concerns identity itself. Most of us imagine ourselves as continuously moving through time. The child we once were seems to have disappeared. The older person we will someday become has not yet arrived. But within the block universe picture, Every version of you occupies its own place in space-time. The curious child taking first steps. The teenager discovering new passions. The adult reading these words tonight. Each exists within the grand structure of reality. None is erased. Each moment remains part of the complete story. This thought has comforted many people, although it is important to remember that it represents one interpretation of modern physics rather than an experimentally proven fact. Still, it beautifully illustrates how scientific ideas can reshape the way we think about existence. Memory offers another intriguing clue. Your brain continuously constructs a narrative connecting countless experiences across many years. Without memory, the sense of a continuous self would largely disappear. Patients suffering severe forms of amnesia often retain intelligence, language, and personality, yet struggle to place themselves within a coherent timeline. This reveals something profound. Our personal identity depends not only on our physical bodies, but also on the information linking one experience to another. Memory is the thread that stitches individual moments into the tapestry we call a life. From the perspective of information theory, this makes perfect sense. Your brain is constantly updating an internal model of reality. Every conversation, every new skill, every place you visit subtly reshapes billions of synaptic connections. The person you become tomorrow is built from information acquired today. In this way, your identity is less like a statue carved from stone and more like a river whose pattern persists even though the water is always changing. Remarkably, modern physics increasingly describes the universe in similar terms. Particles appear and disappear. Stars ignite and eventually fade. Galaxies merge. Black holes evaporate over unimaginable spans of time. Yet information, according to our best current understanding, may never truly vanish. Instead, it changes form, spreading through interactions, becoming encoded in new structures, and participating in the ongoing evolution of the cosmos. This possibility lends new meaning to the phrase we encountered earlier, it from bit. Perhaps reality is not built primarily from solid objects, but from enduring patterns of information. Human life offers countless examples of this principle. A melody survives even when played on different instruments. A story survives across generations through language. The genetic instructions contained within DNA persist while individual cells constantly die and are replaced. Identity often resides in patterns rather than materials. The same may be true of the universe itself. If space-time emerges from quantum information, then every galaxy, every atom, and every living organism becomes part of one vast informational tapestry woven across cosmic history. Entanglement represents one kind of thread, gravity another, electromagnetic interactions another still. Together they create the extraordinary complexity surrounding us. Perhaps this is why the night sky inspires such deep emotion. When you gaze toward distant stars, you are not merely looking across enormous distances. You are also looking into the past. Some of the light entering your eyes tonight began its journey before human civilization existed. Some departed its stars before Earth itself formed. Every photon carries information from another time. Astronomy therefore becomes a conversation across billions of years. The universe is continually telling its own story through light. And we, tiny though we may seem, have developed minds capable of listening. That may be one of the most astonishing facts of all. The atoms inside your brain were forged within ancient stars. The laws governing your thoughts are the same laws governing distant galaxies. The quantum fields describing elementary particles extend throughout the observable universe. You are not separate from the cosmos. You are one expression of it. A small but remarkable region where the universe has become capable of wondering about itself. As our journey nears its conclusion, one final question remains. After everything we have explored, quantum entanglement, relativity, information, spacetime, entropy, and the possibility that time itself emerges from deeper quantum relationships, what picture of reality ultimately remains? In our final chapter, we will gather these remarkable ideas together, separating what science knows with confidence from what remains beautifully mysterious, and reflect upon one of the greatest lessons modern physics has ever taught us: that the universe is not only stranger than we once imagined, it may be stranger than imagination itself, while remaining profoundly elegant in the laws that govern it. The quiet elegance of an unfinished universe. Our journey began with a simple question: what if time is not what it seems? At first, the idea sounded almost impossible. Every clock around us appears to confirm that time flows steadily from the past toward the future. Every sunrise marks the beginning of a new day. Every heartbeat reminds us that life unfolds one moment after another. Our memories stretch behind us, while our hopes reach toward tomorrow. Nothing could feel more certain. Yet science has a remarkable habit of gently questioning the things that appear most obvious. The Earth feels perfectly still, yet it rotates at nearly 1,700 kilometers per hour at the equator while racing around the Sun at approximately 107,000 kilometers per hour. The Sun itself orbits the center of the Milky Way, carrying our solar system through the galaxy at more than 800,000 kilometers per hour. Meanwhile, the Milky Way moves through an expanding universe filled with hundreds of billions of other galaxies. Our senses never reveal this extraordinary motion. Reality extends beyond intuition. The same lesson appears again and again throughout modern physics. Light behaves both as a wave and as a particle. Empty space is alive with quantum fields whose fluctuations never completely cease. Black holes slowly radiate energy. Gravity is not a force in the ordinary sense, but the curvature of space-time itself. And quantum entanglement reveals that particles separated by enormous distances can share relationships that have no counterpart in classical physics. None of these discoveries replaced common experience. Instead, they revealed that everyday experience is only one layer of a much deeper reality. Time may belong to that category as well. Throughout our exploration, we encountered two remarkable revolutions. The first came from Einstein. His theories transformed space and time from separate entities into a unified spacetime. Observers moving differently no longer agree on the passage of time or the simultaneity of distant events. The universe possesses no single cosmic clock announcing one universal present. The second revolution came from quantum mechanics. At microscopic scales, certainty gives way to probability. Particles become excitations of quantum fields. Entanglement binds systems together so completely that their properties can no longer be fully described independently. Each revolution challenged intuition. Together, they created one of the deepest puzzles in science. General relativity describes gravity with extraordinary elegance but treats spacetime as smooth and continuous. Quantum mechanics describes the microscopic world with unmatched precision but introduces uncertainty, superposition, and entanglement. Somewhere beneath both theories lies a deeper description of nature that physicists have spent nearly a century searching for. We do not yet possess that theory. And perhaps that is one of the most beautiful aspects of science. Unlike mythology, science is comfortable leaving questions unanswered. Every solution uncovers new mysteries. Every discovery opens another door. Far from signaling failure, this endless unfolding is the engine of scientific progress. Today, researchers continue exploring several promising paths. String theory imagines tiny vibrating strings replacing point-like particles. Loop quantum gravity proposes that space-time itself possesses an atomic structure. The holographic principle suggests that three-dimensional reality may emerge from information encoded upon lower-dimensional boundaries. Quantum information theory increasingly treats information as one of the universe's most fundamental ingredients. Each approach offers remarkable insights. None has yet earned definitive experimental confirmation. Perhaps future particle accelerators, gravitational wave observatories, quantum computers, or entirely new technologies will reveal the next great breakthrough. History suggests that nature often surprises us in ways we never anticipate. 1 century ago, the existence of black holes seemed almost absurd. Today, astronomers photograph their shadows. Gravitational waves were once considered nearly impossible to detect. Now they have become a new way of observing the universe. Quantum computers existed only in theoretical papers. Today they perform calculations using entanglement inside sophisticated laboratories. What appears impossible today may become ordinary tomorrow. This realization encourages both humility and optimism. Humility, because our current understanding remains incomplete. Optimism, because every generation has expanded humanity's view of reality. Perhaps future scientists will look back upon our own era as only the beginning of a much larger story. Yet even without a final theory, modern physics has already revealed something extraordinary. The universe appears deeply interconnected. Gravity links stars and galaxies. Electromagnetism binds atoms into molecules. The strong nuclear force holds atomic nuclei together. The weak interaction allows stars to shine by governing nuclear transformations. Quantum entanglement reveals that relationships themselves can possess physical significance beyond anything imagined in classical physics. Again and again, nature reminds us that separation is often an approximation rather than an absolute truth. This lesson extends beyond physics. Every atom within your body was forged inside ancient stars. The oxygen you breathe cycles endlessly through oceans, forests, and living creatures. The calcium in your bones once traveled through exploding supernovae. The iron in your blood was born during stellar collapse billions of years before Earth existed. Carl Sagan expressed this beautifully when he reminded us that we are made of star stuff. Modern astrophysics confirms that poetic insight with remarkable precision. The cosmos is not merely our home. It is our origin. Quantum theory adds another subtle layer. Although it would be incorrect to claim that everything remains permanently entangled in the simple way popular culture sometimes suggests, the quantum world demonstrates that relationships can be just as fundamental as individual objects. Increasingly, physicists describe reality using networks of information rather than isolated particles. Perhaps existence resembles an immense conversation rather than a collection of separate things. A conversation carried by photons crossing interstellar space, by gravitational waves rippling through galaxies, by neutrinos streaming outward from stellar cores, by quantum fields fluctuating even within the emptiest regions of the vacuum. Every interaction leaves traces. Every event contributes another thread to the evolving tapestry of the universe. And within that tapestry, conscious life occupies a uniquely remarkable role. Not because humanity stands at the center of creation. Modern astronomy has thoroughly dispelled that comforting illusion. Instead, consciousness is remarkable because it allows a tiny part of the universe to reflect upon the whole. The same physical laws governing distant quasars also govern the neurons reading these words. The same quantum fields filling intergalactic space participate in every chemical reaction inside your body. Across billions of years of cosmic evolution, the universe produced stars, planets, oceans, living cells, nervous systems, and eventually minds capable of asking profound questions about existence itself. That achievement is extraordinary enough without adding mystery where none is needed. Perhaps the greatest lesson of all is not that time is an illusion. That phrase, while intriguing, can oversimplify what physicists actually mean. A more careful conclusion is this: time is unquestionably real in human experience. Clocks measure it. Biological processes depend upon it. Relativity shows that its rate changes with gravity and motion. Quantum theory raises the possibility that our familiar experience of temporal flow may emerge from deeper physical relationships rather than existing as a fundamental ingredient of reality. Whether that possibility proves correct remains one of the great open questions of modern science. And that uncertainty is not a weakness. It is an invitation. An invitation to continue exploring, to remain curious, to appreciate that every answer humanity has discovered has made the universe not smaller, but infinitely richer. Perhaps, in the end, the greatest wonder is not whether time flows, or whether space emerges from entanglement, or whether information lies beneath reality itself. Perhaps the greatest wonder is that the universe is comprehensible at all. That mathematical equations written by curious minds can predict the dance of galaxies, the behavior of atoms, the bending of light, and the whisper of gravitational waves crossing billions of light years. It is a quiet reminder that knowledge itself is one of nature's most remarkable creations. As the night grows still and the stars continue their ancient journeys across the sky, remember that every second you experience is part of a story that began nearly 13.8 billion years ago. A story written in starlight, gravity, quantum fields, and the gentle unfolding of cosmic history. Whether time is fundamental or emergent, whether space-time is woven from entanglement or from principles we have yet to discover, one truth remains beautifully clear. We are participants in an unfinished universe, a universe that continues to reveal its secrets to those patient enough to ask questions, careful enough to follow the evidence, and humble enough to accept that every discovery is the beginning of another mystery. Thank you for joining this journey through one of the deepest frontiers of modern science. Until next time, sleep well, stay curious, and remember that somewhere, even now, photons that began their journey before our planet existed are quietly crossing the darkness, carrying with them another small piece of the universe's endless story.